Ladies and gentlemen, hello again and welcome, coming to you not quite live from One Take Studios, where we kind of have a lot of stuff to talk about today. Our topic today is linear regression and coefficient of determination. I'm going to remove this because most of you don't care about these numbers. There we go. Erasable pen. Kind of cool. Linear regression and coefficient of determination. Essentially what we're talking about today is best fitting line and several of the features that go with that. The concept behind this is structured by a least squares method, which is some calculus stuff, that says that if I have a scatter plot and I'd like to describe the trend behind that, I want to find the line that runs kind of down the center of the dots with pretty much the same number of dots on each side, but I want to be as close to all of those dots as possible. How do I make that happen? So the least squares method says take the distance between each point and your line and turn it into a square. So take the vertical distance, I'm going to switch this to green, take the vertical distance between the point and the line and turn that into a square. Some of my squares may be more or less hideous than others. That one's kind of hideous. Turn it into a square. Again, take that vertical distance between the point and the line, turn it into a square. That one's really hideous. Hopefully you get the idea though. What happens when I turn the distance between, this one's got kind of a double here, doesn't it? When I turn the distance between the point and the line into a square. Well, I'm looking at distance, but the problem is some of these are above and some of these are below, which means some of my distances would be positive and some of my distances would be negative. And if I was trying to figure out distance based on that, my positives and negatives would cancel each other out. By turning these into squares, I am literally squaring them. So whatever this is, I'm going to find the area of this square, and the area of this square, and the area of this square, and the area of this square. If I do that, I will not have any negative values anymore, and I can find the overall total distance between my points and my line. Now, what calculus is doing, and our calculators hopefully are helping us with, is they're playing with this line, saying, what happens if I just scooch this line up a little bit over here? That would make this square bigger, but it would make those squares, in fact all of those squares there, smaller. And so where then is this best line? Where can I put this where I can be closest to the most dots, closest, and make the smallest squares possible? Because if I get this to the place where I can get the total of all of these squares, the total of their areas to add up to the smallest number possible, then what I've done is I've found the line that is as close as possible to all of my data values. Alright, so that is what the calculator is doing. Thank you, Jesus, for calculators. If we run a linear regression, we have a couple of options here. The calculator will do y equals mx plus b, which is what a lot of us are comfortable with. However, you may also want to consider y equals a plus bx, because this is the one that we are looking at usually for statistics. Is it the same thing? Yes, except that here b is the y-intercept, and here a is the y-intercept, here m is the slope, and here b is the slope. But this is the format that we see used in statistics frequently. And the calculator will give us this particular amount. So what I'd like to kind of go with you right now is the process for how I would take a data set and get it to look good on paper. Like where the points go and how to find the line and get it accurate looking. So we're going to start with borrowing some of the calculator stuff here. I have entered a set of data. Oops, not there. Let's go there. There we go. I have entered a set of data, and if you would like to slow down and pause these, you're welcome to do so. I don't want to spend a ton of time with this, but we are talking, there's all my values. It's 8 data points, all right? So feel free to slow that down if you'd like to and put those in your own calculator. You can do that. So I've put a set of 8 data points, and each of these represents, in the X column we have, the weights of cars, specifically the weights of cars in 100 pounds, so 27 is 2,700 pounds, and then their miles per gallon as a result of that. So thinking about this in terms of if the car weighs 2,700 pounds, this is going to be 30 miles per gallon. What if the car weighs more? Well, typically that means that the miles per gallon is going to be less than that. So we would expect to see probably some sort of negative correlation here. What I want to do is actually run that information. So we go to menu where everything fun and exciting is, and we are currently working in statistics, and we would love for the calculator to do some calculations. just because we're in statistics, I'm going to pick our second linear regression option here. It wants to know where the x's are. You can say, hey, the x's are where I told you the x's are, or in column A if you prefer, and the y's are in that second column, or column B. And run. All right, so what does this get us? This gets us a whole bunch of different stuff here. We've got our equation. So we can see from this, scooting up a little bit, the a plus bx, we're talking the a, or the y-intercept, is going to be 43.3. And our b, our slope, is going to be negative 0.67. All right, so this is just like mx plus b. We've got our slope and our y-intercept. The letters are a little bit different. All right, so I'm going to take a moment to jot those down so when I walk away from the screen, I've still got something. So that's going to be 43.3, and that's minus 0.6x is going to be my equation. We have a couple of other values here that I would like you to take a look at and keep in mind, because we're about to be playing with these here shortly as well. Our value specifically tells us about the strength and direction of our correlation. This is called the correlation coefficient. Negative means that we have a negative relationship. As the x's increase, the y's decrease, which we can see in our slope, we can also see in our r value. And because this is relatively close to -1, we're saying this is a pretty strong relationship. The r squared I'm coming back for at the end of this video, so hold on to your hats with that one. It is coming soon enough. I'm going to go ahead and add a page to my document. So Control, add a page, and this time I'm going to go with data and statistics. And if I click to add variable on the x-axis, I would like to tell the calculator, hey, can you put the x's on the x-axis? Because somehow that makes sense. And on the y-axis, could you please put my y values? This is possible because, clicking back over here for a second, I told it the x's were in this column, I told it the y's are here. So because I labeled these, I was able to use those things over here. So this is what my scatter plot should look like. And quite frankly, if I had to draw that on paper, which I'm going to do and show you here in a second, I wouldn't worry about that. That wouldn't be super difficult to do. But what about getting this line in the right place? How are we going to make this happen? Well, that's going to be a little bit extra interesting. I'm scrolling back up. There's our a and our b, our y-intercept and our slope. So let's see here. I want to actually, from this screen, go to menu again. Because from this screen, I can analyze my graph this way as well, which look, we still have regressions on the menu, and we still have the a plus bx as well. This is what my graph should look like when I'm done. And notice it gives me my y-intercept and it gives me my slope as well. I can take and move that out of the way if I want to see it a little bit better. All right, so that's actually not too bad. How do I make this show up on paper accurately? Because we are trying to be accurate, all right? This is not horseshoes, this is not hand grenades, it's not close enough. I would like this to look really good on paper. How do I make this happen? By the way, finding this equation in this screen is good and helpful, but what do you not see anywhere? No r or r squared. So if I want to know my correlation coefficient information, I have to get that from the spreadsheet instead. All right, so one of the things I'm going to tell you is that this line right here, this best fitting line, always has one very specific point on it. If I go back to my original data values and I take the average, the mean of all of the x's and the mean of all of the y's, that is going to be an ordered pair that is on this equation. On this line. So, how might I do that? I could go back and I could add all these up and divide by 8, add all these up and divide by 8. I do want to show you one more thing for those of you that can handle this. I'm going to go back to the menu again, and we are still doing statistics. So there we go, we are still doing calculations. But this time, I want to go back to one variable stats. I'm not running a regression right now. One variable stats. But I would like to tell the calculator that I have two lists. I have a list of x's and a list of y's. And is it going to let me? There we go. So two lists for this. And where are the lists? Can I go back and put the x here? Will it let me? What are my options with this? Oh yeah, there we go. So I've got the x's here, and I've got the y's here as well. Where'd you guys go? There you are. Boom. All right. So I want to run one list as the x's and a separate list as the y's. It's saying, can I put the results in column E? I think that should be fine. We'll find out here in a second. So, okay. All right. So, scrolling. I want to go over this way a smidge. Yep. And then I want to go up a smidge. There we go. All right. Check this out, guys. So, way over here in the screen someplace is my X and Y list. Here's my regression stuff. I can tell because I can see the regression information here. That was my y-intercept and my slope. And now the calculator has run one variable stats twice. Once for my x's and once for my y's. And there is my x bar. That right there, the point 37.38 and 20.88 is a good point to have on my graph. That point will always be on my line. So again, I'm jotting that down right now. 37.38 and then 20.88 is going to be a delightful ordered pair that I definitely want to see on my graph. All right, so I'm going to go back to this guy here for a second. And ladies and gentlemen, take a look at what we've got going on here. These are those points that I was showing you earlier. I have already graphed them, and my scatter plot, fortunately, looks a lot like the calculator's. This is the equation the calculator gave me, and this was that point. This is the x bar, comma, y bar ordered pair. The average of the x's, all the x values, and the average of the y's. This point is always on my best fitting line. Now, while we're talking about notations and things here for a second, this right here is not completely accurate because this line is based on a sample of information. So I need to do this right here. Do you see that? I put a little hat on top of the y. Ladies and gentlemen, this is called y-hat. No, I'm not making that up. Y-hat is the official designation for your equation for your best fitting line. So my y-hat equation is 43.3 minus 0.6x. If I want to put this on paper correctly, I want to get this point in there, absolutely. I'm going to see if I can try red maybe, see how well it shows up. So 37-ish there, 20-ish, so 37, 20, let's see if there's... Right about there, right about there, right about there, right about there. That point, I'm going to change that point into a plus sign. That point is not one of my original data points. That's my x bar, y bar, my means for my x and y. That's going to be on my line. Well, most of us know that you can't just have an equation for a line with one point. You can't draw it that way. So where are we going to get a second point from? Well, we have an equation. So let's use the equation. If you want an accurate line, you want to try to pick something that's farther away as your second point. So right now, if I try to plug in 39, I get something right here. That's going to be awful close, and my line could be a little bit wiggly. So maybe I pick something closer down toward 24. Let's say I plug in 24. So what I'm doing right now is I'm saying, what is 43.3 minus 0.6 times 24? So if I plug in 24 into my equation, it will yield the number 28.9. And I'm going to use that as another point. So 24, 28.9. That's almost 29. That's about right there. Again, that is not an original data point, but it is one that is going to be on my best fitting line. Not using the original data values, but using these 2 points, I am graphing my line. This will be my best fitting line. And that's going to be a good image for it. Alright, so I used x bar, y bar as one point, and I picked another number farther away from x bar, y bar to plug in. If you're looking at this going, yeah, but I don't really see a slope of negative 0.6, and that doesn't look like it's going to go through 43.3, I'm going to tell you right now, please notice that I have breaks in both the x and the y axis. As soon as you put breaks in the x and the y axis, strange looking images just show up here. So please do not rely on graphing slope-intercept form to make this graph. Use actual points, and you will have a much better graph for that. All right, so that's good. All right, we've got all this information. That's good. What do we do with this information? Well, quite frankly, it's used as a model and often used then to predict. So not only have we described this data, but we have set ourselves up with a model that we might use to make predictions. So I might say, okay, I've got all this information. What if I'd like to know, predict the miles per gallon for a, what do we not have here? Let's go 43, because that sounds like fun. A 4,300 pound car. 100-pound. I'm going to do it this way. Well, 4,300. Is that X or is that Y? We said that the car's weight was our driving force here. Driving force. So this is the car's weight. And then this is the miles per gallon up the side. So I've just been given an X value. And I have an equation that will predict what is happening. So if I plug 43 in for X, because this is an X value, we're talking now Y hat. My prediction is going to be whatever 43.3 minus 0.6 times 43 is. And if I run that, let's see here, we're talking 43.3 minus 0.6, oops, wrong button, 0.6 times 43. Gives me a value of 17.5. So we are predicting that if I have a car with a weight of 4,300 pounds, that it's going to have about 17.5 miles per gallon. And if you look at my graph, that's actually not that bad visually. So 43 is about there. 17.5, that's pretty close. That's pretty close. All right, so this is going to be more accurate of a prediction than just eyeballing it off of your line. Please don't eyeball it, but actually use your prediction model, use your equation to put it together and make your predictions. This is actually going to be a reasonable prediction because the number that I was predicting, 43, is within the boundaries of my original data set. So all my values were between here and here, and 43 fits in that range. That is called interpolation. Interpolation, making a prediction within the data set. What if I had a car that somehow maybe weighed 1,000 pounds, which 1,000, by the way, is 1,000. Well, 1,000, that's going to be way over here. That's beyond the edge of my model. Mathematical models are not meant to work for forever, and sometimes, frequently, they get to a point where they don't even make sense anymore. So, if I make a prediction beyond the values that I currently see, that's called extrapolation. And that's going to be a little bit more dangerous because we're saying, I don't know if this pattern continues off of one end or the other, but I'm going to try. And so you can still plug it into the equation. You can still get a value, but it's less reliable. So interpolation is within the data values, and extrapolation is outside of the data values. One more reliable than the other. Okay, so we have almost everything we need here. I know, this is long. But, last thing, ladies and gents, I told you we'd come back to this. The coefficient of determination, which I want to jump back to this screen real quick because, quite frankly, I forgot to write down what that value was. Where's my R squared value? Let's go, where does it go? There we go, this way. And then down. Oh, actually, I should go one more over because that'd make it easier to read. I said over. Thank you. All right, so this thing had an R squared value of 0.89. The R squared is not the same as the R value. Again, this one right here is the correlation coefficient. This one is different. So we are talking R squared is the coefficient of determination. And again, I'm just jotting that number down so I can come back to it. R squared is 0.895. All right. So based on that, we are saying coefficient of determination is R squared. Please be careful with the words. I know it sounds an awful lot like correlation coefficient, but it's not the same thing. The concept is this. Notice we don't have any crazy formulas here. If you're looking for the crazy formulas, in case you haven't figured it out, this is not the video for all the calculus. This is an explanation of what we've got going on. So this is essentially the explained variation divided by the total variation. R squared tells us the amount of variation in the y value that can be explained by your y hat equation, as opposed to 1 minus r squared. So the other piece of that, the complement of that, ooh, there we go, the complement is the amount of variation in y due to something else, something other than our driving forces here. And so this would be something like random chance or lurking variables. This is a little bit hard to grasp. I want to put this in context with you. So again, here's the value that I had on my screen. With the example we were just working with the weight of the car and the miles per gallon for it, the R squared is 0.895. So what does this mean if I put this in context? I am saying that 89.5% of the change or variation of the change in, well, what was my y? That was miles per gallon. So 89.5% of the change in the miles per gallon can be explained by, all right, and so what was the other component of this? That was the car's weight. So we're saying the variation, the amount of change that happens within your miles per gallon, 89.5%, can be explained by the car's weight. As opposed to then, oof, my brain is not going to do this right off the top of my head. Minus 89.5. There we go. That makes more sense. So if I go with the complement of this, the 1 minus r squared, in this case, that's going to be 10.5%, because that actually makes sense. 10.5% of the change or the variation in the miles per gallon is, and I'm just going to say unexplained. Unexplained. So some of the variation that we're seeing, some of the change we're seeing in miles per gallon is not due to the car's weight, but due to other factors that may be random or maybe just variables that we're not currently focusing on. All right, and so that is coefficient of determination, the r squared. This is an example of what that would look like. Example, there we go, based on this stuff from the other page. Okay, read carefully, pay attention to details. Yeah, all right, have fun.